Our next speaker is Iggy Tan, who is Managing Director and CEO of Altech Chemicals Limited.
Battery update. An Australian company has finally cracked the silicon code and produced lithium-ion batteries with 30% higher energy capacity. The company has utilized its game-changing Alumina coating technology that successfully incorporates silicon into the graphite anode of lithium-ion batteries. The result is a 30% higher energy battery with improved cyclability or battery life. This next-generation lithium-ion battery technology is destined for the electric vehicle industry. Tesla has announced that the required step change to increase lithium-ion battery energy density and reduce cost is more silicon in battery anodes. For this to be achieved, high energy capacity silicon needs to be introduced into anode chemistry, as silicon has 10 times the energy capacity compared to graphite. In the words of Elon Musk, this is the most promising anode material. However, metallurgical silicon is unable to be used in commercial lithium-ion batteries today due to two major technological barriers. Silicon expands up to 300% in volume during battery operation, causing swelling, fracturing, and battery failure. The second challenge is that silicon deactivates up to 50% of the lithium ions in a battery. Called first cycle loss, lithium ions are rendered inactive by the silicon, immediately reducing battery performance and life. Industry has been in a race to crack the silicon code. But Australia appears to be at the forefront of the race. This innovative Australian company's game-changing technology delivers alumina-coated silicon particles, which resolves both the swelling and first cycle loss capacity problems. A 30% higher energy capacity battery will mean significant cost benefits to the battery and electric vehicle industry around the world. Phase 2 of research and development work will see the company strive beyond the 30% energy increase. The company has already commenced a pre-feasibility study for a construction of a 10,000 tonne per annum battery materials plant in Saxony, Germany, to service the burgeoning European lithium-ion battery market. And that's the lithium-ion battery update.
Good morning, everyone. Just to give you a background of how a lithium battery operates, as you charge a battery, all the lithium ions go from the cathode to the anode, which you know. And when you discharge a battery, all the lithium ions go back from the anode and the cathode. What a lot of people don't realize that about 8% or 10% of the lithium stays on the anode side on the first charge. And essentially, the lithium becomes inactive to the battery. So what happens? It forms an SCI layer on the first charge, and all the lithium ions that form on this SCI layer doesn't play any part in the future performance of the battery. This is called the first cycle loss capacity. During the operation of the battery, the SCI layer breaks down and exposes fresh sites, so then more lithium is absorbed onto the battery. During the operation, hydrofluoric ions, which is in the electrolytes when there's water around, breaks down the SCI layer and more sites are exposed and more lithium is absorbed onto the battery. So there is a degradation of lithium as you go through the life of the battery. Now, there's a lot of research that's around that shows high purity alumina coatings resolves this problem. And research has been around, not just us, that shows that it reduces the first cycle loss, it improves the cycling stability, improves the high performance of the battery, fast charging capacity, and also resolves some of the thermal runaway problems that a battery has. Interesting research. And for example, this is one of the research that shows a coated graphite battery versus an uncoated graphite battery. After 200 cycles, you can see the coated graphite material has 10% more energy capacity. I mentioned about thermal runaway. Here's a test that shows on the left-hand side, non-coated graphite batteries. And you can see they do a nail penetration test for safety tests. And you can see the picture there, the battery virtually catches the light from thermal runaway. Temperature source about 600 degrees. On the right-hand side is a coated graphite battery, and you can see the battery still intact, and the temperature rises to only 90 degrees. So there are three methods of putting alumina onto graphite material or silicon material. The vapor method, or called atomic layer deposition, the solid method, and a liquid method. Our process is actually a liquid method. And we have the technology to put a very fine layer of alumina around graphite and silicon. It's a 2 nanometer layer. And what that does, it prevents the SEI layer from forming. The beauty of this layer is that it doesn't stop the performance of the battery. So lithium can go through the alumina layer and it doesn't stop the performance of the battery. I mentioned about the hydrofluoric ions. There's a lot of research that shows that the alumina layer absorbs the hydrofluoric ions and turns it to an inert material, so it doesn't impact on the future performance of the battery. So quite a lot of benefits from this alumina coating. So this is some of the material under a microscope. And you can see on the left-hand side, the white layer around it is our 2 nanometer alumina coating. You can see how uniform that is. On the right-hand side is what the industry are trying to do. They're very thick, irregular layers around that graphite material. So our process, we believe, is a cheaper process. It's easier to commercialize. And we use high purity alumina, which has less contamination. And we can adjust the coating of the material. And also because of our low operating temperature, as I mentioned, a lower cost of production. And what we're aiming for is something like this. This is a typical performance of a battery. If we can extend the life of the battery by leaving more lithium ions in the operation, you're going to get an extension of battery life. So let's talk about silicon. As Elon Musk said, silicon is the most promising anode material. It has 10 times the energy capacity than graphite. So in layman's terms, there are 10 times more sites that the lithium can sit on. Now, if it's such a great anode material, why isn't it being used in commercial batteries today? There are essentially 3 problems. First one is that the silicon expands 300% in volume in lithiation and it fractures. Number 2, the first cycle loss, like graphite, instead of 8 or 10%, it absorbs 50% of the lithium onto the surface and turns it inactive. That is a big problem. And the third one is the high fade. If you have less lithium ions, you're going to have less life of the battery. So the industry has been trying to resolve this problem. As I mentioned, this expansion of the silicon particle by 300% in volume, and it actually fractures. Now, what happens is when you have the silicon atom in the anode component, and it fractures, you get delamination. So the material comes away from the copper collector and you get swelling in the battery. That's a big problem. Now, let me tell you the potential of silicon. It takes 6 carbon atoms to hold 1 lithium ion. It only takes 1 silicon atom to hold 4 lithium ions. Now, if this was an anode in a battery and you put some silicon in it, this is how much lithium that battery can hold. You can see the potential of getting silicon in an anode of a battery. Now, what's the potential? Today, graphite is around 370 milliamps per gram per hour. If you can add 10% in that battery, it nearly doubles the energy capacity. Add 20%, it nearly triples it. And if you add 30%, it goes up to about 1,300. Now, what's the impact of that on the commercial side? Here's a Tesla Model 3. It generally runs around 430 kilometers on one charge. If you can add 10% of silicon in the Model 3, you're now nearly doubling the distance on a single charge. 20% will triple the distance, and 30% up to 1,200 kilometers. Now, car manufacturers are not going to give you 1,200 kilometers. You don't need it. They'll go to the 423 Ks and they'll downsize their batteries. And that's the key to dropping the costs of lithium batteries going forward. Now, the way they've resolved it today with silicon is they've gone to very small particles that doesn't fracture. So they've gone to 150 nanometers. The problem with that is the cost is exponential. Our technology uses large silicon particles, and what we figured out was, could we use our alumina coating technology to resolve this fracturing problem? So we did all our test work in-house under the leadership of Dr. Jinwan Lui in our labs. And through our testing of 12 months of development, we've come up with a 30% increase in lithium battery. So this orange curve is silicon and graphite without any alumina coating. And you can see it starts with a high energy capacity, but drops away very quickly because of the fracturing problem. But by coating the graphite and the silicon, this is what we get. You can see it's now a 30% higher energy density anode. And this is a game changer for the lithium battery industry. We announced the news last year, and our lab is working to push that beyond 30%. So our business is virtually buying graphite material, buying silicon material, coating it with our Alumina technology, and putting it together as a product we call Alumina anodes. And we have commenced a pre-feasibility study on a Alumina anode plant, 10,000 tons per annum, in Saxony, Germany. And the reason we picked Germany is because in the state there are a lot of EV manufacturing happening around it. Tesla's built a gigafactory close by, and we're in this industrial site called Schwarzepampe. So on this site, we've also committed to build a pilot plant. And with the pilot plant, we have supply offtake with companies like SGL Carbon, European supplier, and Ferroglobe, one of the largest silicon producers in the world. We have now at least a warehouse space next to us, and essentially we're in the process of constructing a pilot plant. And the reason for that is to get product into the market for the pre-qualification. The plant itself, it's around 137,000 kilos a year, and we've announced that Kuttner Engineering will be completing this. So why we focus on Europe? We believe that the lithium story will be about Europe in the next coming decades. I guess it's fair to say that China, Japan, and Korea has been about lithium-ion batteries, but we feel the European story will take over in the next 2 decades. The reason is there's some 600 gigawatts of battery capacity been announced in Europe. All the European car manufacturers have announced all EVs, and the reason for that is driven by regulation. Europe needs to get to less than 95 grams per kilometer. So European car manufacturers need to average below 95 grams of CO2 per kilometer. If they don't average that, every car they sell will get a fine of up to 2,000 euros. So they have to. And these are companies that have announced that by 2030, 2033, they will go all electric. So, and you can see how much they're spending in that process. BMW, 6.5 billion, Volkswagen, nearly 86 billion, Mercedes-Benz, 47 billion. And so that's why we're focused in Europe. And if you look at the graphite demand from Europe itself, from the 600 gigawatts, it's something like 400,000 tons per annum of graphite. So very exciting technology, and we are in the race to commercialize that technology. Thank you.